Jordan chain of Jordan chain of length k as follows. This is a sequence of non-zero vectors x1, x2, xk, k greater than equal to 1. This is for T in LV. V was a finite dimensional vector space associated with an eigenvalue of T, eigenvalue lambda of T, okay, such that satisfy, or say, let me write if T satisfies this, T of x1 is equal to lambda times x1, T of T of this x2, this is lambda times x2 plus x1 T of x3 is lambda times x3 plus x2 and so on up to xk. T of xk is lambda times xk plus xk minus 1. We could also prove that this chain is linearly independent. This chain is linearly independent. Okay, up to here we could do, right? Let us start now. What I could say about this. We now shall be proving the existence of Jordan canonical form for T. And we just got this information from here. The maximum length of this chain can be the dimension of V. Maximum length can be dimension V over F, that is N. And in that case, the matrix of T with respect to that basis, which is a Jordan chain, would be of the kind I just told you. It is lambdas on the diagonal and ones on the super diagonal, and rest are zeros. This is what we could see. Okay. Oh. That was the matrix of T with respect to that basis is lambdas here and ones here and zeros elsewhere. All right. Let us now prove the existence of Jordan canonical form for T. Right. So for that, this is theorem. Let T belonging to VLB, dimension of V over F is a N, right? If let me write CTS. If CTX splits over F then V has a basis, which is disjoint union of Jordan chains. Or in other words, the matrix of T is a block diagonal matrix with blocks as Jordan blocks. All right. This is known as the Jordan block of length n. If this is k by k, then this is also denoted by, such matrices are also denoted by j, k, lambda. K is the order of that. Okay. Right. Let us prove this. Proof. So we shall be proving this for all transformations operators which are nilpotent. Assume P is nilpotent. Nilpotent means there exists a least positive integer m such that t raised to the power m would be 0. Okay. And we shall be proving this result by induction. We shall use induction to prove this. All right. So first assume that dimension of V is 1. Since T is nilpotent, if dimension of V is 1, then obviously T would be 0. T is 0 operator. And in that case, nothing to prove. The result is holding trivially because T0 means the matrix of T would be 0. Okay. And that is a Jordan matrix, Jordan block. Okay. So if suppose the dimension of V is not 1, more than 1, we shall be assuming the result to be true for all the vector spaces which are having dimensions less than n. All right, less than n. So here we shall be now assuming this is the result is true in this case. Assume that the result be true for all vector spaces with dimension less than or equal to n minus 1. So here, since the dimension of V is n, therefore we have T a non-zero nilpotent operator. Okay, then we can talk of a range of T, or say image of T. Image of T. Let me just write here, image of T. Okay, image of T. This is a T. This is a T invariant subspace of V and image T is not identically 0. This is because of T is non-zero nilpotent operator. Therefore, this is non-zero. Okay. All right. Oh, what is happening here? Non-zero. All right. This is a subspace of T. So obviously this is nilpotent. Certainly would have something in the kernel space which is non-zero. So the dimension of this image T would be certainly less than n. Certainly less than n. And therefore, by induction hypothesis, therefore, one more thing, but what I want to say, this is T invariant subspace. So I can have an induced operator T dash. Therefore, by induction hypothesis, T dash, which is an induced operator. Induced operator of T has disjoint union of Jordan chains. Disjoint union of Jordan chains.
So what is T dash?
T dash is an induced operator of T on this image T. Is it all right?
Okay.
All right. Since I cannot talk of T here, T dash is an induced operator which is on image T and the dimension of image T is less than n. Therefore, this T dash has disjoint union of Jordan chains on this vector space. And let those be as B1 dash, B2 dash, Pk dash. So I can just take that B dash here, B1 dash union B2 dash union B3 dash and so on union Bk dash. All right. What that means, these union means the matrix of T dash is a diagonal matrix with Jordan blocks on the diagonal. Okay, with respect to these chains. All right. And B dash, each B dash, Bi dash is containing vectors xi1, xi2, and so on, xi and I. All right. What is the action of T dash on these vectors? T dash, when applies on T xi1, this is same as T of xi1, which is certainly 0 because Jordan chain, by the definition of Jordan chain, first vector is an eigenvector. Here eigenvalue is 0. So this is 0 times xi1. All right. And Txij would go to T dash xij is T of xij, that is equal to, yes, xi j minus 1. This is true for all j's starting from 2 to ni. All right, because this I, so ni. And I ranging from 1 to k. Is this okay? Are you getting my point? Hello?
Yes,
hello
sir.
Ah.
Yes, sir.
So this is the meaning of the Jordan chain. So what I could conclude here, that in every chain, that means first element in all BIs, that BI dashes, that is going to 0 under this T dash or
Why,
T.
sir?
Okay.
Why?
Hello.
Why is it happening?
These are Jordan chains. See here. This is what the Jordan chain mean. And in the case of nilpotent, this is 0. Lambda is 0.
Okay.
Okay.
Yes, sir.
Yeah. So that means the first element in each of BI here is none other than the part of the kernel of T. That means that is x11, x21, and so on, xk1. These are linearly dependent and in kernel of T. All right. Kernel of T. And if they are in the kernel of T, then I can just have these elements. I can extend this set to a basis of kernel T. Right? So extend the set x11, x21, xk1 to a basis of kernel T by adding more linearly independent vectors.
Hello.
Hello, as yeah. Hello.
How they are linearly independent?
Jordan chains are always linearly independent.
But this is not one Jordan chain. These are the first elements of all the Jordan chains.
Yeah, yeah. So, and you have already seen that if something, this is a set, linearly independent set, all right?
Mm-hmm.
And if you pick one element from there, that is linearly independent.
Yes.
All the Jordan chains, these are linearly independent basis.
Yes.
This is a basis of image of T dash. And basis means they are linearly independent elements.
Yes.
All right.
All right. Thank you.
So
Hello.
these elements are in kernel as well as image, right?
Yeah, basis of image of T. Image of T dash.
But the image of T dash is contained in the image of T dash. Image of T dash is contained in image of T dash.
We are not concerned with that. We are only concerned with image of T dash. That may be contained. Yes. Okay. But we are not at all concerned with that. Since they are the part of image of T dash and are linearly independent. So I can take a sub part of that, which consists of x11, x21, xk1. These are linearly independent, but in kernel T because of this reason. All right.
Yes, sir.
And I can extend this to a basis of kernel of T by adding some more vectors, which are as follows. Here I just take x11, x21, and so on, xk1, xk1, and then I just add, say, y1, y2, and this way yq elements to this, which just completes the basis of kernel T. All right. Hello. Hello.
Yes, sir.
Okay. Could you get my point?
Yes.
Moreover, one more thing which you are to notice here, xi and I. This is the last element in bi dashes. All right. This is the last element in bi dashes and contained in image of T dash. All right. What is the meaning of this? That means there exists xi ni plus 1. I just take ni plus 1 move in V such that T of xi ni is exactly xi ni plus 1. Oh, sorry, xi ni plus 1 here, but this is because this is in image. So I must be showing here. Yeah, xi ni plus 1. This is here. All right. Hello. Image T means there exists a vector in V such that when T dash applied on that would give me xi ni. Is it okay?
This is T dash.
T dash. Yeah. T dash. Right. T dash means T also. This is also T because this is an induced operator. Right. So what I can now conclude, now I can have, this is what is going on. Let me see if this gets, yeah, I must be writing here. Then it would be, oh, wrong. And
But sir, T is not guaranteed, you know?
yeah.
Because the vector xi ni plus 1 is coming from V, not from the subscript.
This is not a part of bi dash.
So can we
This is
write
not
it
a-
like T xi ni plus 1?
This is because this element is in each bi dash, which is a part of image T dash. Therefore, there exists one element in V such that this gives me as xi ni. Right? Hello.
Yes, sir.
All right.
Yes.
Now what I just take, I take B as union of bi dashes, which are, let me take B, not bi dashes, bi's now. What are those bi's? I just notice here. What is happening? Oh. Let me just cancel this. It is not erasing. So let me write this. B is union of bi's, I ranging from 1 to K plus Q. What are BIs? Let me now BIs. Let me just explain these BIs. All right. Something is happening to this file. I do not know. It is getting translated in the next sheet. BI dashes are BI dashes union. This is what I just got, this element. This is from I1 to, I1 to K, or I ranging 1, 2, and up to K. Then I just take BK plus I as simply YIs. Here I ranging from 1 to Q. Just look at this and convince yourself. Is it all right? Hello? Hello? Hello?
But
Yes, sir.
you are taking xi ni plus 1 from V. But
these are BI dashes, as
domain of-
earlier we have taken. I just add one element which I just taken from here.
No, the above V, that xi ni is belongs to beta I dash. That means it is contained in image of T dash. That means there exists a vector xi ni in the above page.
Yeah.
So,
Yes.
xi ni plus 1 V. I mean the domain of T dash is something less than V.
This is in the domain, but I am not looking at as this as a image or domain. Now I just defined my BI. Sorry, this is not BI. B. This B. This is the union of I1 to K plus Q BIs, where BIs are equal to BI dashes union this vector and BK plus I. This is simply containing singleton element, which is YI for I1 to Q. Any doubt up to here? I just take now this set B. Hello?
पर ऊपर वाले पेज में जो xi ni है वो इमेज ऑफ टी डैश के अंदर है. तो आपने बोली तो हम लोग ने लिया कि xi ni plus 1 मिलेगा इस समय v के अंदर such that image of xi ni plus 1 under t dash is xi ni.
Yes.
t dash का तो कुछ वो सब स्पेस पे इंड्यूस्ड ऑपरेटर है v के.
हाँ
तो
जी.
वो xi ni plus 1 हम v से कैसे ले रहे हैं? वो तो
अल्टीमेटली
मतलब वैसे तो v पे आ जाएगा.
Finally, I am to switch to V. I am not to stick on image T dash.
तो हम सब इस पे इसको डायरेक्टली ऐसे देख नहीं रहे हैं.
मैंने ये एक सेट उठा लिया अब. I just picked up this set B, which is union of these, where BIs are containing these elements for I1 to K, and BK plus I containing singleton elements, which are YIs. Up to here, I just now this is what we are defining this set. That's it. No need to see image T dash or so. Is it all right?
Yes, sir.
This part would be coming into the picture a little bit later. You just see this part, how that is coming into the picture. Now I claim that this B dash, this B is a basis of B. How can it be a basis? It will be a basis if I can prove that the cardinality of this is exactly the dimension of V, 1. Second part, all the elements of this V, they are linearly independent. Is that all right? Hello? Hello? Hello?
Yes.
Yes, yes, sir.
So cardinality of this B is none other than, look at here, this is the sum of the cardinalities of Bi dashes I1 to K plus how many elements I added. You just look at. Q elements are these and how many elements? K more. So this is K plus Q. Is it all right? Hello? Hello?
Yes, sir.
Now you just look at what is that? This is K plus Q. Is it not dimension of image of, this is dimension, image of T plus this is kernel, dimension of kernel of T. This part is dimension image of T. This part is dimension kernel of T. Is it all right? See, these Bi dashes are disjoint. Therefore, I can just take the sum of cardinalities of Bi dashes here. And one more distinct element added to each Bi dash, which just makes this as Bi, I1 to K. And singleton element is taken in Bk plus I, which is Yi. These are Q elements. So total cardinality of B would be coming out to the cardinality, sum of the cardinalities of Bi dashes plus K plus Q. And this is obviously the dimension of image of T, and this is the dimension of kernel of T. Is it all right? Hello? Hello?
Yes, sir.
This is all right?
Yes, sir.
And this is the dimensional formula. T is a linear operator. If T is a linear operator on V, then the dimension of V is same as dimension of image of T plus dimension of kernel of T, which is N. Hence, this cardinality is equal to N, which is dimension of V. Now, what is left to prove? Only thing is left to prove that the elements in B, they are linearly independent. That is, B is a linearly independent set in V. That would lead to that this is a basis of V. All right. So let us prove the linear independence. So let us take this sum, which is I ranging from 1 to K and J ranging from 1 to N I plus 1. Yeah. This is alpha ij xij plus this another sum, which is having R1 to Q, yeah, beta R into YR, which is 0. Because these are the only elements which have been taken in the linear combination in B. All right. If we consider this linear sum to be 0, then we have to prove that all alpha ij's and beta i's, they are zeros. So apply the operator T on this. What we get? We get now. We get what happens when you apply T to this. This is a part of kernel of T, so 0. One more part which would be going from here. What is that part? Can you just tell me what is that part? Summation I ranging from 1 to k. Yeah, alpha ij x ij. What should I take here? Summation. When this j is 1, you just see xi1 is in the kernel T. So here that would go when you apply this kernel part, that would be 0. So this is 0. This is only left when you apply T on this. Is it all right? Hello? Hello?
Yes, sir. Yes, sir.
Now what can you say? Now you see this is 0. And what are you getting out of that? It's not giving you alpha is j's are zeros. Alpha is j's are zeros for j starting from 2 to ni plus 1. And I starting from 1 to k. Is it all right?
Sir, does this will be xij minus 1?
Let me check. 1 minute. This j, what are you saying? Yes, please.
Yes, sir, does this will be xij minus 1? Alpha ij xij minus 1.
No. I just started it from 2 to ni plus 1. Because I just see here. What is with me? These are the part of kernel T. The second subindex is 1 for all elements in bi dashes which are in kernel T. So therefore they are killed under T. So j here would be then starting from 2 instead of 1. What I just take here, j starts from 1 to ni plus 1. It would start from 2. Okay. And therefore, these alpha ij's are 0 because that is a part of basis. Right? Now, if this is 0, then what is left with me? This me. Let me write this. Not write this. I'm just doing something. When you applied T on this, then this part would lead to 0. All right. This part would lead to 0. Is it okay? But these here, these xi, hello.
Yes, sir.
Here, these xij's are linearly independent elements. Therefore, these alpha ij's are zeros for all j starting from 2 to onward, and I plus 1, and I start from 1 to k. Is that okay? If this is 0, that means what is left here? I just left here for j1 index. That is it. Alpha I1 xi1 plus this beta r and yr starting from 1 to q. This is equal to 0. This initially I took that 0. When you operated T on this, I get this 0. and this 0 means I get these alpha ij's are zeros because of linear independence of these xi's. All right. And then what is left in the original linear combination is this. Now you check. These are the elements of basis of kernel T. Kernel T. And therefore, these alpha I1s, what I'm getting, yes. These alpha I1s, that is 0 along with beta i's for all i's. Here, let me not write this beta here. For all i's, yes, for all I 1 to k, and beta r's 0 for all r's. That means this set we have taken here, B, that means this is a linearly independent set. All right. This proves, this proves B is a basis of V. What this B consists of, this is containing B1 union B2 union BK union BK plus 1 and BK plus Q. Right? What is B1? B1 is B1 dash union XI X1, yeah, 1 and 1 plus 1. All right. B2 is B2 dash union X2 N2 plus 1 and so on. And this B K plus 1 is containing only Y1 and BK plus Q contains YQ. Is that okay? Now this is this and all BI dashes, they are disjoint. This is also disjoint. So they are basically disjoint sets. And are they not forming the disjoint unions of the Jordan chains? BIs are disjoint Jordan chains for T. Check. Is it not so? Hello? Hello?
Yes, sir. Yes, sir.
Are they Jordan chains? If so, then that means the T, which was non-zero nilpotent operator has disjoint union of Jordan chains, right? Jordan chains. Disjoint union of Jordan chains. And hence, I could prove the result for nilpotent operator. Nilpotent operators. For general T, what is happening with me? 1 minute. Hello. So let us now discuss the case of general operator T. See, CTX splits and so MTX would be of the kind x minus lambda 1 raised to the power say n1 or m1 whatever, x minus lambda 2 raised to the power n2 m2. Let us just take m2 and I have taken there m2 and x minus lambda k as mk, and that means you just have V decomposed into these T invariant subspaces, primary decomposition theorem. All right. And now each Vi has an induced operator of T, induced operator Ti, let us say Ti. Okay. Ti. Ti induced operator of T on each of Vi, which is T invariant subspace, right? Now we must talk of Si. Si is what? Ti minus lambda I of I. What can you say this Si? This is a nilpotent operator. Why? Because of this is Ti minus lambda I is the minimal polynomial of this Si is exactly T. Sorry, let me write here. Ti, this is minimal polynomial of MSX. This is x minus lambda I raised to the power mi. Therefore, this is nilpotent operator. And for every nilpotent operator, we have already seen the case, the above case settles this problem for each SI. Okay. If this settles for each SI, then the matrix of T would be a block diagonal matrix with blocks as Jordan blocks of these Jordan chains of lambda. All right. SI, if the matrix of SI just which is containing zeros on the diagonal, then matrix of Ti would be containing lambda i's on the diagonal and rest are ones. So what can I say? The matrix of T with respect to this basis would be Jordan block here with respect to lambda 1 some order. Again, it can be repeated also. All right. So how many this is some R1, or say this is RL, this is lambda K, and rest are zeros. This is the matrix, and this is that basis which we are looking for. That completes this Jordan basis, the existence of the Jordan basis in this case. Is there any doubt? If you have any doubt, ask me, please. Right. Let me now just start with something more here. You look at this matrix. Can you say something about this? Hello. I just now switch to the other problem. So I ask about the determinant of this. Let us see here. 1 upon where eta is and lambda is are distinct. Distinct. Real or complex numbers.
Hello, sir.
Yeah.
Isn't it just a scalar where lambda is and nu is are scalars?
These are scalars. Yes. This is what I'm just saying. Distinct.
It's not a matrix actually, sir.
This is a matrix. I just take ij starting from 1 to n.
Okay.
This is a sequence of eta is I ranging from 1 to n, and this is a sequence of lambda is I ranging from 1 to n. Now you look at this is a matrix. This matrix is of the kind, if I just reduce the order, let us take this is 2 by 2, then it is 1 upon eta 1 minus lambda 1. This is 1 upon eta 1 minus lambda 2. This is 1 upon eta 2 minus lambda 1. And this is 1 upon eta 2 minus lambda 2. If I ask you this, can you just look at the determinant of this? The determinant of this is very easy. You can find it out. Let us just find out the determinant in a logical way. See here, what I can do, this determinant is same if I operate R2 minus R1. So what I get finally, determinant would not change when I apply this operation. Okay. 1 upon eta 1 minus lambda 2. Here what entry I would be getting after subtraction. So this entry would be probably, yeah, lambda 1 would be cancelled. So this is eta 1 minus eta 2 upon eta 2 minus lambda 1 into eta 1 minus lambda 1. Is it so? And this entry would be again same way, eta 1 minus eta 2 divided by, yeah, eta 2 minus lambda 2 into eta 1 minus lambda 2. Is it so? Are you getting this? Hello?
Sir, yes.
Yes. Is it so? Hello?
Yes, sir.
So what I can just take out, this part I can take from this column, and this part I can take out from this column. So what I get is 1 upon eta 1 minus lambda 1 into 1 upon eta 1 minus lambda 2. Here I get, this is 1, 1, and this is 1 upon eta 2 minus lambda 1. This is 1 upon eta 2 minus lambda 2. Yeah. Once again, I can do this one operation. I can apply operation subtract column.
Eta 1 minus eta 2 as well.
Where?
Take common from that second row.
Eta 1 minus lambda 2. Yes, that is, I am taking eta 1 minus lambda 2. Is it so?
No, sir. Eta.
Where? Eta 1 minus lambda 2 is common. Yeah.
From numerator of second row.
Numerator. Eta 1 minus eta 2. Right? Then again I can apply one more operation to this, which is C2 minus
C2 minus C1.
Yeah. Apply that and I get this factor out. This is already there. So what is I get? Let me just call this star. I get this 1 upon eta 2 minus lambda 1. This is 0. What about this? This would lead to eta 2 cancelled, and I get this is lambda 1 minus lambda 2, I think. So divided by both factor eta 2 minus lambda 1 into eta 2 minus lambda 2. Is it so?
Yes, sir.
And finally, what I get, the determinant would be eta 1 minus eta 2
into lambda 1 minus lambda 2.
Yeah, I just do that. Eta 1 minus lambda 1. This is eta 1 minus lambda 2. Here I get lambda 1 minus lambda 2. And divided by this, eta 2 minus lambda 1. Also one more factor, eta 2 minus lambda 2. Eta 2 minus lambda 2. Is it so?
Yes, sir.
This is the determinant. All right. So utilizing this part, I would be now sharing you my slides for the next problem. What is that? Just look into this. Yeah, I share now this. Yeah, view full screen. Is it visible?
Yes, sir. Yes, sir.
Okay. So here we shall be proving wheel interlacing inequality on one-dimensional perturbation of permission matrices using fundamental technique. Right? What are those? Look at that. This is a problem of variational principles for eigenvalues. It was discovered in connection with the problems of physics. One of the famous works in the Theory of Sound by Lord Rayleigh. This book was published originally in 1877, but reprinted by Dover in 1945. The classic book on modern applied mathematics is Method of Mathematical Physics by Courant and Hilbert. These are the replete with applications of variational principles. You can see several variational principles in these. Okay. So in this lecture, we shall be now considering two interlacing sets of real numbers, right? And would be realizing those two sets of interlacing real numbers, interlacing sets of real numbers as the eigenvalues of the Hermitian matrices A and one of the one-dimensional perturbation of the A. Perturbation means if we add something scalar times a one-dimensional projection means this is P scale equal to P, all right? Then what happens to the eigenvalues of the P? That we are now looking at as the interlacing of these two sets of the real numbers. See here. This is the first lemma which I just want to share with you. If we have these two sets of the real numbers, number one is lambda is, number two is eta is. They are like that. All right. And if I look at this matrix, n by n matrix, and see its determinant would be coming out to be that. I have proved this result for 2 by 2, and the same is true for 3 by 3 and so higher orders. Can you easily see this at your own?
Yes, sir.
Can you see this? See, I have just done this for 2 by 2. Now you can see this for n by n. All right. If you just have any doubt, I can show it to you where I could see. See this.
It will be lambda 2 minus lambda 1.
Yeah.
Lambda 2 minus lambda.
Anyway, you just make that correction. Oh, no problem. Just I made these calculations for you just to see how can I just find out the determinant of that. All right. You just look at the calculations at your own, please. Okay. The determinant would come out to be like that. Calculations is exactly same as that of in the case of 2 by 2. If you have any trouble, then I can do it for you. Okay. Then using this, if Zi, Xi, and T be complex numbers, then determinant of T would be exactly this, where dz is a diagonal matrix with the diagonal entries as z1, z2, zn, and x is a column vector consisting of the components as x1, x2, xn. All right. Is the statement okay with you? Hello? Hello?
Here.
Are you just clear with the statement? What I wanted here? Determinant of diagonal matrix minus T times x star, where x is the column vector given by the components x1, x2, xn. And then x star would be a matrix n by n of order n by n matrix with entries x1 mod x1 square in the first row, x1, x2 bar, and so on. So the proof of this, we can just see by continuity argument, we can just assume that Zi, they are non-zeros. They are non-zeros. If any of the Zi is 0, then I can replace that 0 by Zi plus epsilon with epsilon very small, positive number, right? And now you see, if Zi's are non-zero numbers, then if I take x as 0, this would be 0. And the determinant of the diagonal matrix would be simply this. So in case x has 0, the determinant is okay. That is true, right? Then we come to assume that x is non-zero. And in that case, x star x would be a scalar number, which is k. X star is now a row vector with conjugates of xi's, and x is a column vector containing components as x1, x2, xn. The matrix P, if you look at this is a projection of rank 1, right? The rank of the matrix is 1. And projection means P square is equal to P. You can check it. All right. If not, then I can do for you. Here, what is P? P we have taken x. X star is a row vector. X is a column vector. This I take k, and P is taken to be 1 by k x star. Is that okay? Hello?
Yes, sir. Yes, sir.
P square. P square is 1 by k. This is k square x star, and then x star. You see this x star is k. Yeah, k would go with k, and therefore I left with 1 by k x star. Is it so? This is equal to k.
Yes.
So this is again P. Okay, as per my definition of this. So this is a projection. Such matrices are known as the projection. Okay. Right. Then since Tz, look at this equation now. I just multiplied two expressions of this kind. Tz, dz inverse x star, Tz inverse x star, which gives me what? By associativity, I can have this part out. From here, I just take x star with this. I just take this part. All right. You take this part and this part. Leave out x star to this side and take x star into this side. This part is taken out because this is a scalar. Why this is a scalar? Hello? Hello?
Yes, sir.
This part is a scalar. Do you agree with that?
Yes, sir.
Yes, sir.
So
T,
can we take T x star d z inverse x?
X is a scalar. Yes, sir.
No. This total is a scalar.
Multiply with T also.
Yeah, T is already a scalar.
Yes, sir. Yes,
T
right.
is a scalar, so x star dz inverse x comes out to be scalar.
Scalar. Yes, right.
Yes.
This is out. See here, I just took two matrices. One is this. This is, let me call this M matrix. This is another M. So this is M square. If I just call this scalar as alpha, this is M. So M square is equal to alpha times M. What does that mean? If I call this as M, this is M into M. This is some scalar. And this is again M. What do you mean by that?
Eigenvalues and eigenvectors, sir.
No. Something you are nearby, but not answering exactly to me. Let me
And
just
sir, one more thing, sir.
let me now first explain. What I could see in that, I just multiplied one matrix M with M, and I get alpha times M for some alpha. What does that mean?
Columns of M are its eigenvectors.
No. I don't need that. I need something else.
So if we solve this,
Sir,
we
it
will get
satisfy m into alpha minus m equal to 0.
Yeah,
Yes.
this is 0. What does that mean?
So the eigenvalue can be 0.
No. The minimal polynomial of this m is none other than this.
Yes, sir.
This is the minimal polynomial of m. Okay. Let me write here x. Is it so?
Yes, sir. Yes, sir.
So that means the eigenvalues for this m are alpha and zeros. That's it. Is it so?
Yes, sir.
Now it
Yes.
must be very clear to you.
No,
See,
sir.
this is m square is equal to alpha times m.
Hello, sir.
Yes, please.
Sir, why it has to be actually minimal polynomial? It could be some annihilating polynomial of m, no?
No. We don't talk of annihilator here now. It is m is a matrix now. I'm just looking at a matrix equation. M square is equal to alpha times m. Right? M is a n by n matrix. Annihilator, when you talk of the annihilator, then you have to talk in the vector space case. We are not talking of the vector spaces here. I'm just playing with the matrices here.
Okay.
All right?
Yes, sir.
This is the minimal polynomial of this matrix. And can you just explain now what are the eigenvalues of this matrix M?
One eigenvalue should be 0.
That is sure, not one rather.
And
you should say something else. Only one non-zero eigenvalue.
Its rank is 1, sir.
Rank is 1. Therefore, this is the only non-zero eigenvalue, which is, yes, who was speaking this? This is the only non-zero eigenvalue of that, and rest are all zeros because the order of this is n by n. Therefore, n minus 1 eigenvalues would be 0.
yes, sir.
Okay.
Yes,
and
yes.
if I just add identity to this, one means identity, or say subtract identity from that, what can you say about the eigenvalues of this? The eigenvalues of m are lambda is, what are the eigenvalues of I minus m?
1 minus lambda.
Yeah, that is what I'm just asking. So if I just write I minus this m, this is exactly a matrix of this kind. Okay. And the eigenvalue for this m are known to me, which is one of the eigenvalues is this, and rest are 0. Therefore, this matrix I minus this m has one of the non-zero. Sorry, these are all non-zeros. One of the eigenvalue is this, and rest are all ones. Rest are all ones. One is 1 minus non-zero that, and other is 1 minus zeros. All right?
Yes.
So one eigenvalue is given by this, and rest are ones. Okay. And therefore, what is the determinant of this?
Product of eigenvalues.
Which is this product of these two matrices, and determinant of product of two matrices means product of the determinants. One
Yes,
is
sir.
I know this is diagonal product of the diagonal entries, which is Z1, Z2, Zn, and the determinant of this we have already seen here. Eigenvalues, they are all known to me. The determinant of the matrix is none other than the product of the eigenvalues.
Product of eigenvalue, yes, sir.
And that is what we are taking here. Okay. These are the eigenvalues. And this expression is none but this. And you just place here. All right. And that proves this result. Done?
Yes, sir.
Yes, sir.
Then we come to the main part of our result. See, this is the set of interlacing numbers. Interlacing numbers means they are lined between each other. Lambda 1 less than equal to eta 1 less than equal to lambda 2 less than equal to eta 2 and so on, less than infinity. Then we are to realize two matrices. One is A, whose eigenvalues are exactly lambda is, and the other should be a perturbation of A, one-dimensional perturbation of A, which has exactly eigenvalues as eta j. This is what I wanted. So see here, how can we prove this? The fundamental techniques, we shall be only using fundamental techniques. So I can, without loss of generality, A as diagonal matrix with lambda 1, lambda 2, lambda. I could take, can you think of the matrices here? If I just remove the condition Hermitian. Hello?
Yes, sir.
What are those matrices?
B is equal to A minus.
No. Forget about that. I just ask you, you just remove the condition Hermitian. Can you find out two matrices whose eigenvalues are lambda is and the other matrix has eigenvalues eta j's?
Other matrix.
Diagonal matrices.
Diagonal is 1 lambda is, but I just remove the condition Hermitian.
Upper or lower diagonal?
How?
A minus trace of.
If I choose my A and B are the companion matrices of the polynomials whose roots are lambda is and eta is, then easily you can write two matrices which are non-Hermitian. All right. But I put here condition Hermitian. Therefore, what is I need? I need to see this also. Right. So first I assume my A as diagonal lambda is, which is Hermitian. Right. Then I am to choose my matrix B such that it should be A plus TP, where P is one-dimensional, rank 1 projection. Rank 1 projection. So what is the need? T must be in that case certainly trace of B minus A, which is eta I minus lambda is. All right. Summation of eta is minus lambda is, that should be the scalar T chosen here. Okay. But I do not know about P. To choose my P, what I do, I take my P as.
Sir, can you please show the last?
What one? This?
Yeah, this one. Just for a minute. So you are assuming A to be diagonal using the. How you are assuming A to be diagonal matrix?
Because I am to just get two Hermitian matrices whose eigenvalues can be realized as lambda is and eta is, where the other should be a perturbation of the first one.
Can you please go to next slide?
Yeah.
So here you are assuming that without loss of generality, we can assume A to be diagonal, right?
This is an easy way to choose.
That is by the spectral theorem you are assuming, right?
No, easy way, because diagonal entries are not other than the eigenvalues.
Yes, sir. Yes, sir.
And this is Hermitian also.
Oh, okay. So for diagonal, we can do it for sure. That is this slide says, right?
I can trivially take it.
Okay.
So for the existence of B, my T should be none other than the trace of B minus A. See, if I am to choose my B in such a way, then T this, I am to choose T also. Then there exists T greater than 0. So for that T, I have to take T as trace of B minus A, which is this. So only thing is not known to me, which is P. in this case, that P, suitable P should be chosen such that etas are the eigenvalues of my P. Is that okay? So if I choose P as xi bars, xj bars with ijth entry of this matrix P, and the sum this is equal to 1, that means P I have chosen as x star, where x is a column matrix with components as x1, x2, xn. All right?
Yes, sir.
Yeah. Then I am to now search out these xi's. My problem is to find out these xi's, right? In such a way that the eigenvalues of this B should be exactly eta I. And the eigenvalues of B should be exactly eta is implies the determinant of this matrix should be 0 for all k 1 to n. All right. That means the determinant of this matrix should be 0. If I just put here everything, A is diagonal lambda is P times P is this, then this expression means determinant of this matrix is 0. And if I just take this as my one Z1 and this as my Z2 and this as my Zn, using just this theorem which I proved here, determinant of this is given by that, apply this here, I can get the determinant of this as this. Okay? And what this determinant says, the strict inequality, we can choose these lambda is nowhere equal. If they are equal, I can add epsilon to that. This is known as continuity argument. Okay. And then take in the end as epsilon goes to 0. So this determinant 0 means we have this expression for all k 1 to n. And this system of the equations would have solution only if the determinant, non-trivial solution, only if the determinant of this coefficient matrix is non-zero. Coefficient matrix, this. This system can also be written like this. This system, these are n equations, k1 to n. And this system can be written like that.
X star A. Yes, sir.
Okay. Okay. All right. See this system.
Yes, sir.
I have written this system to this. See, easy. Because otherwise 1 by t, you are getting here everywhere 1 by t. T inverse is out. I just make them 0. What I did, I just apply elementary row operations on the left side of this equation and just subtract row 1 from each of the rows. And I get something out from there which are multiplied here. And so I get zeros here. So this system can be written like that easily. Right? And this system further can be improved this way, where U is some invertible matrix written in between that. And if you take this as U, then U inverse would be what? You add them, one added here, and rest are identity. Okay. And this U would be then multiplied with this, and U inverse would be multiplied by this. The system, this can now be seen as this. Any doubt? So this system. Okay. And further, this system can be further resolved, making these zeros. Here also, this would be now ones and these are zeros this way. All right. And these are all positive quantities because lambda 2 minus theta 1 is positive. This negative would be settled here. This negative would be settled here. This negative would be settled here. And if I apply my induction to the system of linear equations, this to the solution of equations of this, here I can just get the solution of this submatrix, means x2, xn are obtained, and the first equation would give me x1. They give me the solution x mod x1 square, mod x2 square, mod xn square. They give me rather positive solution using induction hypothesis here, right? Once you get these xi's, that means you get the required p, which is to be found out. This is a simple problem. Just I placed before you to understand the things. How can you play with the matrices? See, so this B is exactly that matrix which is having theta is as its eigenvalues, which is a perturbation of matrix A, right? In some of the let me now show you the this completes the problem. Okay, once you get mod xi squares, you can get xi's. Hello.
Yes, sir.
Once you get mod xi squares, you can get xi's. Complex numbers you can get. Okay. Now you can see the references. If you look at these references here, you can find out the same solution to this problem, but using a complex analysis in that, which is not that easy. Other ways to look at the submatrices, you can also look at a book which is by Rajendra Bhatia, Matrix Analysis. There you can see such problems. All right. And you can find out, but those are not that easy. Here we are simply using this plus minus techniques and matrix multiplications. That's it. You try to solve these equations, you would find the easy way to reach out here. Okay. And that's this, what I just stated to find out B and A. If you have any doubt, ask me, please.
Yes, sir. Sir, my question is, what motivated them to choose T is equals to trace B minus A?
Hello, pardon, please.
Yes, sir. I'm saying why they have chosen T is equals to trace B minus A. Means what prompted them to choose this?
You see, I am to take my B as this.
Yes.
If I am to take B as this, then P times P would be B minus A.
Yeah, right.
And P is a projection. Okay. The trace of the projection is one only.
Yes.
So if I just take trace operator on both sides, then obviously T is known to me, which is trace P minus A.
True, sir. Okay.
If you don't take this trace as T, then you may not be able to find out this T here.
Okay.
Okay. That is bound to be taken as trace of B minus A. Yeah.
Yes,
any other? Any other? Okay, then it is all right. This is the complete part of what I would say. We shall be doing some examples of the Jordan forms in the tutorial class. Okay. Hello.
Okay.